Hi everyone, my name is Sean Griffin, and welcome to the pre-seminar for University of Washington's Combinatorics seminar. The main talk will focus on several families of rings with connections to combinatorics, and the coinvariant rings are one such family. So I'd like to focus on those in the pre-seminar in order to motivate the results in the main talk. So first, let me talk about the combinatorics. In particular, the inversion statistic on permutations. So we'll let Sn be the group of permutations of the letters 1 through n. And then given a permutation pi, we'll let an inversion of pi just be a pair of indices I less than j, where the permutation is out of order. And inv of pi will be the number of inversions of pi. So for example, if pi is 4312, then the first and the second positions are out of order because the 4 is greater than the 3. And similarly, the 4 and the 1, and the 4 and the 2, and the 3 and the 1, and the 3 and the 2. So the total number of inversions for this permutation is 5. And one nice thing about the inversion statistic is that it has a really nice generating function. So if you sum up over all permutations of q to the number of inversions, it has this really nice product formula where the ith factor is just the sum of the powers of q up to q to the I with n minus 1 factors. And you can see this easily from induction. So if pi in one line, if you write pi in one line notation and look at where the position of n is, say there are I letters to its right, then n will form an inversion with all of those letters to the right of it. So if you let pi prime be the permutation obtained just by deleting n, so the permutation on the letters 1 through n minus 1 obtained by deleting n, then the number of inversions of pi is just the number of inversions of pi prime plus I. So q to the inv of pi is q to the inv of pi prime times q to the I. So if you run over all I, you'll see that you get the factor on the right. Since I can go from 0 to n minus 1, and then by induction, as you run over all pi primes, possible pi primes, that gives you the other factors. So you can make this precise using induction. And so how could we get an algebraic interpretation of this fact? So let me introduce the cone-variant rings Rn. So the symmetric group acts on the polynomial ring in n variables just by permuting the variables. So sigma xi is x sigma of I. We'll denote the polynomial ring just by q bracket xn for short. And we'll say that a polynomial ring we'll say that a polynomial is symmetric if it's invariant under this action. So if you permute any two of the variables, it's invariant. And as an example, one of my favorite family of symmetric polynomials is the elementary symmetric polynomials. So this is where you take a positive integer d, and E sub d is just the sum of all the square-free degree d monomials. So for example, E2 of x1, x2, x3 is x1, x2 plus x1, x3 plus x2, x3. And we'll consider the following quotient where we write down the ideal generated by all of the positive degree homogeneous symmetric polynomials. So this is the ideal generated by positive degree symmetric polynomial, homogeneous symmetric polynomials. Which is otherwise known as the invariant ideal. And we'll consider this quotient, and we'll call Rn Rn is called the coinvariant ring. One misconception is that this ideal contains, that everything in this ideal is symmetric. That's not true. Since it's an ideal, you could have, say, x1 times E2. That's in the ideal, but it's not symmetric in the variables. We're just taking the ideal generated by those. And this coinvariant ring has a really nice presentation in terms of generators and relations. So since it's an ideal in this polynomial ring, it has to have a finite number of generators. And a really convenient generating set is just all of the elementary symmetric polynomials. So it's generated by E1 through En. And it may not be obvious at first, but this quotient ring is actually a finite dimensional Q vector space. We've modded out by enough things to make it finite dimensional. And here's a quick proof of that fact. So let's start with this identity, algebraic identity. Yeah, I mean, the relation's just meaning like, so, okay, I guess I just misspoke. I just mean like, you can write it down in terms of a quotient by an explicit ideal with an explicit set of generators. Sorry about that. I didn't mean like, here are all of the relations on the E's. Yeah, sorry. Yeah, presentation as a quotient ring is what I mean. I see, okay. So here's a quick proof of the fact that it's finite dimensional. Take this identity, so if you take the product over all of the t minus xi and expand this as a polynomial in t, then, for example, if you took all t factors from, if you take t from each factor, then you'll get t to the n. Or you could take n minus 1 t's and then a factor of minus xi. You sum up over all of that, you get minus e1 times t to the n minus 1. So this is the sum of all the variables. That's the e1, and so on. So you can write it in terms of the e's. And then all you have to do is plug in t equals xj for a fixed j. And then on the left-hand side, you'll get 0 because t minus xj was a factor. And on the right-hand side, you'll get tj to the n minus e1 xj to the n minus 1, and so on. Oops. And so this is telling us that xj to the n, I forgot that it vanishes when I go to the next slide, but it's telling us that xj to the n can be written as a sum over all of these, like ei xi to the xj to the n minus I, which is in that ideal. And so xj to the n is 0 in Rn. So this tells you that Rn is spanned by a finite set of monomials, the monomials where the power of each xi is at most n minus 1. And you might ask, okay, is this set of monomials is a spanning set, but is it a basis? And the answer is no. So how could you find a basis of monomials? Well, Emil Artin figured out that you could take a subset of these monomials to get a basis. And he wrote down this set of monomials where the degree of the ith variable, xi, is at most I minus 1 for all I. And it turns out, and he proved that it represents a basis of this coinvariant ring. And as a corollary, you can immediately see the dimension of Rn. So I guess by this inequality, you have to have x1 to the 0 as a factor, or like, yeah, you have to have x1 to the 0. But you could have x2 to the 0 or x2 to the 1 in your monomial, and so on. So there's one choice for x1, two choices for x2, and so on. So the dimension is the number of these monomials, which is n factorial.
Oh, wait, is it also included that all the AI are distinct?
No, they could be the same. You could have x, like one has to be in the set of monomials.
Well,
I just mean like there are two choices for the power of x2. There are three choices for the power of x3, and so on.
I. Okay, right. Okay, yes.
Yeah. So I choices for the power of xi.
It still seems like there's some relations in there though, like we have x1, we can pick that by setting a1 to be 1 and the rest to be 0. We can get x1 that way. And we can also get x2.
Wait,
and then
what do you mean?
If we set a1 to be 1, I minus 1, I'm sorry.
Yeah, so, right, so for I equals 1,
yeah, I'll stop talking now. Sorry.
So it's equal to 0. Yeah, so you have to have x1 to the 0 in your as a factor in your monomial. Okay. Yeah, and you can see that you can always eliminate x1 from a monomial because the sum of the variables in this quotient ring is 0. So you could write x1 as the minus the sum. Minus the sum of the other variables to get rid of it. So it makes sense that there should only be one choice for x1. And so to relate this back to the formula we had on the first slide, we need to look at the Hilbert series of Rn. So recall that if you have a graded vector space, so if V is a direct sum of VIs, where VI is the ith piece, and suppose that VI is finite dimensional for all I, then its Hilbert series is just the generating function over the dimensions of the graded pieces. So you take the sum over the dimension of vi times q to the I. And in the specific case of v equals Rn, this quotient ring is graded by total degree in the variables, because the polynomial ring is graded by degree in the variables, and we're quotienting out by a homogeneous ideal. And if we take a closer look at Artin's monomial basis, then it immediately tells us what the Hilbert series is. So since we only had one choice for x1, we had to have a1 equals 0. That contributes a factor of 1. We had two choices for the power of x2. It could either give us like a factor of 1, or it could raise the degree by 1. That corresponds to the 1 plus q and so on. And you can see that this recovers, or this refines the dimension formula that we had earlier, the n factorial formula, because if you set q equal to 1, the left-hand side just becomes the dimension, and the right-hand side just becomes 2 times 3 times, and so on up to n. And for that reason, we're going to call this 1 plus q, 2 bracket sub q, is called the qified number. So the q analog of the number 2 is 1 plus q. The q analog of 3 is just the sum, 1 plus q squared, and so on. And we'll call this whole product the q analog of n factorial. So to connect this with permutations, though, let's look at the Garcia-Stanton basis, and we'll discover some more combinatorics along the way. So there's an alternative basis for this coinvariant ring in terms of which encodes the combinatorics of the major index statistic. So let me define the major index. So we'll let capital des of pi be the set of descents. So that's just the set of indices I, less than or equal to n minus 1, where the value of the permutation descends. So if pi I is greater than pi I plus 1. And the major index of pi is just the sum of all of the descents. So for example, if my pi is 4132, then the first position is a descent, and the third position is a descent. So the major index statistic of pi is 1 plus 3, which is 4. And then given a permutation, we'll define this monomial, the Garsia-Stanton monomial, denoted by GS sub pi, which is just the product over all descents, where you take the monomial, the product of the variables x1 through xi. So in our case of pi equals 4132, GS pi is, well, there's a descent in the first position, so that's x1. And then in the third, so we do x1, x2, x3. And from this, you can see that the degree of GS pi is exactly the major index statistic of pi. So what does this mean for the Hilbert series? Oh, so, and theorem, Garcia in 1980 proved that this set of monomials, GS pi, does actually give you a basis of Rn. And then you can see, okay, what does that mean for the Hilbert series? The Hilbert series is really just the generating function over the degrees of these monomials in my basis, which is just, as we said on the last slide, is just q to the major index of pi.
Can I interrupt and ask a question?
Yep.
So there are, to me, many permutations that have the same descent set. So isn't the way you've defined GS pi going to give you the exact same monomial then?
Oh, maybe
I thought you had to take
I think,
x of w2.
was this supposed to be pi 1? I think this was supposed to be pi 1.
Yeah.
Okay, sorry about that. Okay, this is actually x4. Yeah, you're right. x4, x1, x3. That's better. Thank you, Sarah. Yeah. Okay, so this gives you an algebraic reformulation of an identity of McMahon that in bin Madge are eco-distributed on permutations. Okay, so as the last part of this pre-seminar, I also wanted to connect Rn to some geometry. And usually you might see a geometric connection to the complete flag variety. I'd like to give you a different geometric realization of Rn, which is maybe less well known, but it has more connections with the main talk. So this will be in terms of the nilpotent diagonal matrices. So here's some notation. GLN is the set of n by n matrices with rational entries. And then n is the set of n by n matrices whose nth power is 0. That's just the set of nilpotent matrices. And we'll let T be the n by n diagonal matrices. And observe that if you take these two sets, n and T, and you take their set theoretic intersection, the only thing in that set is the 0 matrix, because the only diagonal matrix which is nilpotent is the 0 matrix. So set theoretically, this intersection is not very interesting, but we'll see that Rn actually encodes. So basically this statement is telling you where n and T intersect. What I'd like to tell you is how Rn encodes how those two sets intersect, how those varieties intersect geometrically. So a little bit more notation. Q bracket GLN is the coordinate ring of GLN, n by n matrices. That's just a polynomial ring on the variable entries. And we'll let I of n be the defining ideal. That's just the ideal of polynomial functions which vanish on n. And then observe that, okay, the entries of x to the n all vanish on that set because that's how n was defined. So we know that this ideal generated by the entries of this nth power is contained in the defining ideal, but it's not equal. So the not equal part is important. And to see that, why is it not equal? Because if x is nilpotent, then the trace of the matrix has to vanish. And that's a degree 1 relation. I mean, that's a degree 1 element of the defining ideal. which is not generated by the entries of these nth powers because all of these entries are degree n. So there's a little bit more in this defining ideal. And in order to find that ideal, you have to use some linear algebra. So look at the characteristic polynomial. By definition, this is the determinant of t times the identity minus the matrix. And we'll expand this in terms of the powers of t. And we'll let sigma I be the coefficient of t to the n minus I. And observe that a matrix is nilpotent if and only if all of its eigenvalues are 0. So if it's nilpotent, then this polynomial is actually just t to the n, which means that all of these sigma i's vanish for positive i's. And it turns out that the defining ideal is generated by those sigmas. And to get to the intersecting with the diagonal, so Kostin observed that, well, if we specialize x to be diagonal, so diag of x1 through xn, so if those are the diagonal entries, then sigma I of x is the same as the ith elementary symmetric polynomial in the variables. I mean, so by the entries of x to the n, I just mean take the nth power of the matrix, and each entry is a polynomial in the entries of the matrix. And okay, so if you specialize, you'll get back the elementary symmetric polynomials. And Kostin proved that, and basically Kostin's observation can be translated in the following way. So we'll let Q bracket n intersect T be not the defining ideal of the intersection, but this quotient ring where you quotient out by the sum of the ideals of those two sets. So usually when you're taking the defining ideal of a variety, you have to put a radical here. So I'm saying don't take the radical. Instead, just quotient out by the sum of those ideals. And he proved that Rn has an alternative description as this coordinate ring. This coordinate ring of, another name for this is the coordinate ring of the scheme-theoretic intersection. Okay. And essentially this is saying that Rn is really encoding geometric information about how those two varieties are intersecting at the origin. And let's see, how do I do this? So I made a graph. Where is it? Oh no. I made a graph somewhere of this intersection, but now I don't know how to get to it. 3D calculator. Okay. We don't have time to go through the calculation, but it turns out that you can identify for 2x2 matrices, you can basically identify n with this equation, the cone. So this is in 3 coordinates. And then when you intersect with the diagonal, that's intersecting with this line. Let me see if I can spin it. And if you can see, the intersection is, set theoretic intersection literally is just the origin, but it's intersecting in a funny way. You'd say that it's intersecting with multiplicity 2. Yeah, so it's another way to say it is it's a fat point because basically the Zariski tangent space of the cone is 3-dimensional, but when you cut it with this line, you get a 2-dimensional space. So it's a multiplicity to intersection. Okay, so that's all I had to say for the free seminar.
Thank you, Sean. So yeah, does anyone have any questions?
I have a question. Are the Garcia-Stanton polynomials or monomials related to Schubert polynomials?
I'm not sure, but I think that, so if you take a Schubert polynomial and you take the rev-lex leading term, I think that's related to, Sarah probably knows this better, either the Artin basis or the Garcia-Stanton basis. I don't remember which one.
Okay, thanks.
It's the Artin basis.
It's the Artin basis.
I know there's no connection between the Garsia-Procesi or Garcia-Stanton monomials and Schubs.
But there is some Carlson and Oblomkov wrote a paper recently on affine Schubert calculus, and they had some connections to the Garcia-Stanton basis. So maybe you can find it in that paper. It's called Affine Schubert Calculus and Double Coinvariants.
Cool, thanks.
Okay, well, if there are no more questions, let's thank Sean again.